So what Herman didn't mention is that I came to MIT as a postdoc to work with him. So no, I'm very happy that I'm able to come and visit you all today. So I'm going to be talking about low frequency earthquakes and why should we care about them and what they can tell us about the plate coupling dynamics in subduction zones and other plate boundaries. And so what you're looking at here is a cartoon of the subduction of the Wanda Fuca plate, the North American plate. And so what we're going to be thinking about today is if you look along the plate interface here, we get here in this transition zone, and I'll talk a little bit more in depth slides. We have what we call these low frequency earthquakes. And you're looking at here 2.5 years on the y-axis. You're looking at the inter-event time or recurrence interval of these low frequency earthquakes. That means that every time another low frequency earthquake happens, we measure the time in between, and we plot it here on the y-axis on the logarithmic scale. And what we see is that the activity in this transition zone is very clustered. And by that I mean that there are swarms of low frequency earthquakes where the recurrence intervals decrease. And so we get a big group of activity all at once. And they happen in these very well organized clusters. And so we're going to be using that throughout the talk to understand what's happening. So the plan of the talk today is to tell you what plate coupling is, or at least how I think about it. What are low frequency earthquakes? And then what can they tell us about plate coupling? And then the last part, you're my test subjects today, because this is a paper that's in revision and I haven't presented it yet. So I'd be happy to hear feedback on this last part about what we think controls the dynamics of low frequency earthquakes and plate coupling. All right, so to get going, we're going to start with our cartoon subduction zone, where we have the oceanic slab subducting beneath some continental plate. Here, like I said, it's the cartoon of the Cascadia subduction zone. And if we are far from the trench, where pressures and temperatures increase as we go down dip along the subduction interface, the plate interface is hot and ductile, and so it basically continuously creeps underneath and past the continental plate constantly. And the important thing that we'll be thinking about here is when that's happening, the plate above it is oblivious or has no idea what's happening beneath it because there's no friction or contact. There's no there's no frictional contact between those two plates that would try and move the upper plate. So when it's creeping, the upper plate doesn't even know what's happening. If you get closer to the trench, so now you're at lower temperatures and pressures, here you're in a frictional regime, and we expect that we have this locking between the two plates, where the downgoing oceanic slab wants to go down, but it's frictionally stuck to the overlying plate, and so it drags it along and builds up elastic strain energy until it breaks. So if we were to look at shear stress through time on this interface, it would be building, and once it reaches some failure threshold shown by the dotted line, we would have an earthquake. And then what happens after that is that we repeat the cycle over and over again. So this is sort of a cartoon model of what the seismic cycle looks like, where you have this frictional locking that allows elastic strain energy to build up until it's released in a big earthquake. So how do we observe this? So one way to do this is by looking at deformation at the surface with geodetic measurements like GNSS or GPS. And so the first thing we'll look at here is now we've changed the shear stress to surface displacement. And we're looking at the surface displacement at a GNSS station, this green triangle far from the trench. And we see that nothing's happening. We're in the stable plate interior. Whatever subduction is happening beneath it, it's oblivious to it because there's just continuous creep. And there's no sort of frictional locking that might register an elastic signal at the surface. If, however, we move our GNSS station closer to the trench, now you can see that the surface displacement is being dragged landward, so away from the trench into the plate interior, because of that frictional locking that's dragging the continental plate landward as the oceanic plate wants to subduct. Until, of course, we have our earthquake, and the GNSS will jump back in the other direction towards the trench, and then the cycle will continue after that. So we can use geodetic observations to get some idea of how the plates behave. So how do we quantify this? Rather than just phenomenologically looking at the GPS time series, how do we actually get some sort of number about this? And the idea here is that if we can quantify this, that we're able to compare different places and compare the degree to what to their capability to host earthquakes. So if we think that frictional locking is allowing for the buildup of stress, that we might have a higher chance to have a big earthquake. So we do that by quantifying the plate coupling, what it's called, or this frictional locking. And this is purely a kinematic observation. We typically think of frictional locking, but there are questions about the mechanisms at play here. But it's very simple. In this reference frame that we'll use here today, we're going to measure this gamma just as a ratio of the observed velocity at the plane interface, or slip rate at the plane interface, versus the one that we would expect, or VM, the modeled plate rate. So there you go. This is what we would expect at the surface, at the denominator, and then the numerator what we actually observe. And like I said, this depends on your reference frame, whether you're fixed in the plate interior or you're on the conducting slab going down, but it doesn't really matter for our purposes here today. So this coupling we can measure varies between 0. So that would be that it's completely uncoupled. And so that would be the case if we're looking at the creeping portion of the subduction interface, and here you would expect no surface displacement, just a horizontal line. Between fully coupled, where the observed velocity that you measure is the same as what you expect, and then everything in between. So how do we observationally measure this? Now that we have some sort of definition that we can operate with. And we're going to do that with with geodetic motion of the surface. And we're going to be looking at the Hickory subduction zone. So this is based on work that a former postdoc of mine, Louise Bourgon, was doing in New Zealand. So we have the Pacific plate that's subducting beneath the North Island of New Zealand on the Australian plate, and it's monitored by all these red dots, which represent GNSS stations. And they've had this continuous network operating for more than 2 decades now. It's a really wonderful data set. It's also been monitored since 2015 by radar imagery, like the Sentinel-1 satellite from the European Space Agency. And so there with radar, you can also capture the rate of surface displacement, and we can use that to infer what the coupling is at depth. We have more than enough geodetic data to constrain plate coupling. And so what would we actually do if we go through an example here? So here I'm trying to do the time series of this one point here. We would expect that loading or the buildup of stress would be going towards the west because the Pacific plate wants to drag New Zealand to the west, and its friction stuck to it beneath it. So that's what you see here on this east-west component. So we can go back to our definition of plate coupling. We can put the denominator here on the figure and say this is the velocity that we would expect if we had a fully coupled plate interface. We can then fit a linear trend to our observations and say we observe the same thing, and we would come away and say we have 100% plate, coupled interface around this GNSS station. Just as simple as that. We can do the exact same thing for the radar or INSAR data, where we are looking instead of at vertical north, south, and east, west motion. We're looking at motion in and out of the line of sight vector from the satellite as it goes past and takes the radar image. And then we can take all of these observations together and we can invert them in sort of a standard inversion for slip at depth. That can be as as little or as more complicated as you'd like. And we can resolve this plate coupling, this map of plate coupling across the plate interface. So here what you're looking at in colors, from 0 to 1, you have the plate coupling. I haven't talked to you about negative plate coupling, but here plate coupling is just the velocity that we infer from the surface data normalized by the denominator, or the expected plate velocity. So if it's going in the opposite direction, because let's say there was an earthquake, we have negative plate. But in reality, it's just us normalizing our observations with our expectation. So we can see that we have spatial variations. It looks like, there's one big part of the Hickory interface that's very coupled. Of course, it's always difficult to resolve coupling when we don't have data. So if we are far offshore, close to the trench, we don't have GPS stations there. And so our resolution is going to be poor there. Of course, there's seafloor geodesy, which I won't really get into here today, but that can, contribute very important perspective on what's happening close to the trench, where we expect our biggest earthquakes and tsunamis to happen. And then, here, what Louise was working on was integrating INSAR into these coupling models. And so there we can see the differences between the models where we just have GNSS, or we have GNSS plus INSAR, and we can see that there are some big differences that we think are meaningful. So why do we think that this is, an important thing to do? And, we're not the first people to do this. This has been done for years now. Is that it gives us an idea of where the plate is building up shear stress and where we would expect big earthquakes to happen. So if we go back to our model that we had before, if we look here in the middle of this coupled region, we'll probably have something where the GPS would be doing this, and we would have some seismic cycle at some point once the big earthquake happens. And so we have a fully coupled interface. We can just go straight down dip of that point until we reach where we expect this continuous creep to set in because of temperatures and pressure that increase. And we would expect no coupling, and so the GPS wouldn't see it. And so, this just corresponds, the southern section corresponds to our cartoon model just flipped to get the geometry or anti-subduction. But, there's unexpected variability, let's say, or that's not predicted by a cartoon model, where if you're completely coupled here and you move along strike, all of a sudden you find at the same depths where you would expect the same pressures and temperatures, you have a completely uncoupled interface. So there's all sorts of reasons why you could expect this to be the case. You could expect maybe, this actually is the case, is that there's very different amounts of sediment that gets entrained into the subduction, depending whether you're the northern or southern part of the Hickory subduction. You might have a fluid that might be subducted with those sediments, or metamorphic dehydration reactions that might release fluids, and that might change the frictional behavior of the interface, or maybe just the temperature is different because the spreading rates are different and you have a different, a temperature of the slab that goes down. Then you also have these places, we've already sort of explained kinematically at least what we would expect for fully locked and fully uncoupled. But there's also everything in between, which physically is also sort of hard to explain because there might be some continuous component of motion, but then the rest experiences a stick-slip cycle, so that's not also very obvious. Could just be a result of spatial or temporal averaging, just because our geodetic data, the resolution of it isn't as nice as we'd like it to be. But regardless of all these sort of complications, we can still use this map in a productive way and say that if we have this big patch here, like a 200 by 200 kilometer patch that's building up tectonic stress, that could result in, let's say a magnitude 8, we believe, or we use earthquake scaling to figure out what that might be. But the problem here that we're going to be talking mostly about today is we took this observation here over a certain time period. And that observation will change if we change the time period over which we estimate that velocity. So here we might expect 100% coupling if we take this time period. But if we now take a longer time period, and I'll just show you how that changes, we would expect a smaller velocity, because we have these wiggles, these ups and downs in the time series. And so if you look at the coupling down dip of that lock zone, it changes by quite a bit. And so it reduces the area by about half, and that changes then the earthquake that you'd expect. So getting this right and understanding what we're measuring when we're estimating a velocity that will then inform our inversion for plate coupling is important. And so we have questions about what's actually happening when this is wiggling back and forth. So what's actually happening here is we have slow slip. So we have motion that goes eastwards, that's opposite to what you would expect for like a signal of frictional locking. And they last over, here over a few months and here over multiple years. And so what is this slow slope? And why do we think it's important for what's happened near the seismogenic negatives? So here we're now looking at a map view of the Cascadia subduction zone. in the northern US and western Canada. And these squares represent different GNSS stations. And so we're looking here at this one at the tip of southern Vancouver Island. And here we have subduction going this way, so we expect on this east-west component that loading should go eastward away from the trench until eventually an earthquake makes it go backwards. And so here you can see that loading right here, and then we have this reversal of motion over about 3 weeks, and then it starts marching back in the expected way, expected direction once again. So this is a slow slip event, that reversal of motion. It can last from days to weeks to months. It can release just as much stress as a big earthquake, but this happens down dip typically of where big earthquakes are going to happen. So what you're looking at here is in blue, these two different blue colors. They're showing you the amount of slip that's happening at the plate interface. I don't remember, but it's several centimeters over this wide, broad area. And each of these stations now, you can see two vectors. The red vector is the estimated displacement at that station during this 3-week period. And in yellow is the predicted displacement from this model. And so you can see we can fit the data pretty well by putting about, several centimeters of slip over a broad region on the subduction interface, just beneath the megathrust where we have frictional locking. And so if we're interested in how this megathrust is going to be loaded, it's not being loaded continuously, it's being loaded intermittently or episodically by these slow slip events that are happening again and again and again. So what's cool about this from a geophysical perspective is instead of having to wait, tens to hundreds of years for the next earthquake, we can actually see multiple cycles of these over our human geophysical timescales. So here you're looking over about 7 years. This one event that we see here is this one right here. And we can see that this happens in northern Cascadia, at least, about every 14 months. So we can see this thing repeat over and over again. And this is telling us that stress being built here by slab pull, by the negative buoyancy that slab falling into the mantle, loading this area that's somehow frictionally locked, that then breaks or fails over 3 weeks and loads the mechanism of difficulty. So there's actually seismic activity that accompanies slow slip. So we changed our squares to circles, and these circles are now seismometers. And this is a 30-minute window on these different seismometers in the same place. And what they're showing you is a signal that we call tectonic tremor. It's very noisy. There's no clear phases, like T or S waves, that we would be able to identify and located precisely in time and space. So these noisy emergent signals. But if you just, put a broadly defined window when you think there are windows of time when the tremor is happening and you add them all up, this is that second y-axis here. You can see that tremor peaks. The tremor activity peaks every time there's a slow slip event. So this tremor is happening at the same time as slow slip, but it's affording us or giving us the opportunity to see it slow slip potentially at much higher resolution. Anything we do on a seismometer that's recording at 100 hertz, we're going to be able to resolve things at shorter time scales than our GPS time series that are typically resolved on daily time scales. But the problem with tremor is that without identifiable seismic phases, it's difficult to characterize and it's a bit frustrating. Thankfully, however, within tremor, there are these little discrete seismic events that we'll be spending a lot of time looking at today that are called low-frequency earthquakes. All right, so what you can do is you can take a tremor waveform that's here over, 30 minutes or so. You can zoom in on one of these big impulsive spikes within it and look across 10 different seismic stations that are close to it. And you can see this noisy S wave arrive. And you can then pick that S wave and you can locate that low frequency earthquake in a way that you cannot do with the tremor. And you can see that this is happening over just several seconds instead of 30 minutes. And so you're able to catalog and identify these low frequency earthquakes with much more precision. And if you do, you're trying to understand the seismic waveforms better, you can figure out that they are these shear events that happen on the plate interface. And what you see, and this is the thing that I showed you on the first slide, the most important characteristic is that they're repeating over and over and over again. So when I showed you this figure on the first slide, you sort of took my word for it that these things are happening in these bursts or clusters. But what this is actually showing you is that every single one of these dots is us identifying in the continuous seismic record these waveforms, these exact waveforms with this exact move out that suggests that it's coming from the exact same place. And so this is giving you a time history of a single source location on the plate interface that's radiating these seismic events over and over and over again with the exact same focal mechanism. And the rate at which it radiates is very well correlated with slow slip. So if we look here at a GPS time series over 2.5 years, and we just make this motion before we just remove a linear translate, it's flat. And then we see this big slow slip event that 4 centimeters of displacement at the surface. We then take the LFE activity that happens in the same place, and instead of we take the cumulative counts, or just the counting events from normalized from 0 to 1, and we remove that trend at the beginning, just in the same exact way we did it for the GNSS time series, and we find that they're extremely well correlated. So we see that nothing's happening in the LFE activity or the GNSS surface motion, and then they all, for the same duration, jump up over about 6 months. So we can sort of take a step back already and ask ourselves, what are low frequency earthquakes even telling us? Because we know that we have this geodetic information that's telling us we have these broad slow slip events that release, that slip tens of centimeters over several weeks or months. Yet within that, we have these little tiny seismic events that happen over and over and over again. And so this is already telling us that on the plate interface, we have some sort of heterogeneity of how the interface behaves. So we typically talk about this as rheology. And the idea is here that this, the fact that these processes happen together is probably not an innocent coincidence, but that they're telling us something about how the plate interface actually behaves. So this is one of the coolest figures that unfortunately I never made. This is Alan Rubin and John Armbruster from a paper 2013. And they're showing you the exact same data twice. And the only thing that's different between these two panels is they just change the order in which the data are plotted, the colors are plotted. So what they're showing you is the low frequency earthquakes that happened during 3 different slow slip events that happened 14 months apart in 3 successive years. And so here they're plotting blue on top, red underneath, and green at the bottom. And here they're plotting green on top, red in the middle, and blue on the bottom. And so what you see is that the exact same locations on the plate interface with this very precise location method are generating the exact same events from one slow slip event to the next that are separated by 14 months. So this, this is like ripping off the continental plate and being able to actually look at the interface and what's happening. So this is just extremely cool, showing us that there's this persistent heterogeneity that is telling us, or that is responding to these slow slip events in multiple cycles in the exact same way. So this is just, for me, this is mind-blowing. Yeah, okay. So we can then ask ourselves the question, so what makes LFE so special? And this should be, okay. This is something, if I had time, I would show you about, but I don't. So I'm going to skip this. There we go. So this is the work that former postdoc King Wong did with me. What she did, and I won't go into the gory details, is she did some source analysis of the seismic signals themselves, and she demonstrated how if you carefully use earthquake above and below where the LFPs, the low frequency earthquakes are happening, you can tease apart what that low frequency earthquake source looks like. And so here these are just source time functions of 2 earthquakes that come from almost the exact same place as low frequency earthquakes. And then this is the low frequency earthquake itself. And you can see these are all supposed to be the exact same, about the same moment magnitude. But that the source duration of the low frequency earthquake is much longer. So there is something about the plate interface that makes these earthquakes behave differently than typical earthquakes. And we think that, fluids are playing a strong control on that seismic source process. And we can start to think about, if we have, these observations placed in context of what, Alan Rubin and John Armbruster showed in that top figure, we can start to think that maybe the distribution of pore pressure that allows for low frequency earthquakes might not be the same everywhere in the plate interface. And so it's clear that heterogeneity plays a strong role. And so you can go and see like what a geologist thinks of a subduction channel, and it's anything but simple. There's all sorts of different material that have been could be entrained sediments that have been subducted. It could be part of the oceanic crust. It could be underplated from the continental plate, and all of these things have been deforming for millions of years before they actually get down to the depths where slow slip and low frequency earthquakes happen. So everything must be a mess there. And heterogeneity has to play, heterogeneity in both material and how that material responds to stresses has to play a big role in controlling slow slip. Okay. So you can actually look at, one of these outcrops, these exhumed outcrops that geologists love to do their work on because they're also complicated and there's all sorts of cool stories they can tell with them. Is whether it be in the Franciscan in California or in exhumed outcrops in Japan, they constantly see these metamorphic rocks, and they always see these veins. And so one thought when we think about low frequency earthquakes is that these veins are developed by cycling pore fluids through them and depositing quartz and then remobilizing them when it starts to shear again. And so you might imagine them as LFP, low frequency earthquake slip surfaces. And maybe one way we could explain why they're so low frequency is that maybe we have limited extent of the actual slip surface, but we have many of these slip surfaces that slip together. And so we might in that way generate a seismic source that doesn't look like a single fault that breaks that will generate a typical earthquake, but might generate something that looks more like a low frequency earthquake. And so, you have to just imagine these are, what you actually see underneath the outcrop. This is what it might look like in situ in the subduction interface. And we have these low frequency earthquakes and slow slip all happening in this. All right. So now, what can low frequency earthquakes tell us about plate coupling? So this is work that a student of mine, did a few years ago. But the idea is that if LFEs are sharing the same fault in the slow slip, can we use the seismic record to basically predict the geodetic record? What can that tell us? And can that allow us to access short time scales that we would otherwise be unable to see with geodesy alone? So the idea here is we have two observables that we want to connect with some sort of model that uses that leverages the same physical quantity for both the data sets. So what we're going to do is convert our geodetic time series or geodesic displacements to slip on the interface, and we're going to do the exact same thing for this low frequency earthquake activity. We're going to change it into seismic fault slip at the interface. So first for the geodetic data. So now we're in Mexico, and you're looking here at the central Guerrero segment, where you have these slow slip events, these magnitude 7.5 that happen every 4 years. And we have 3 GNSS stations that are aligned sort of in a long big profile. And I'm plotting over 1 year what the displacements look like. And you can see that they start more or less about the same time, but they have different amounts of slip. You can see here the red one that's furthest down dip has less slip than the one that's furthest up dip that has the largest amount. We know something about the fault geometry from seismic imaging. And so what we can do is we can take the expected split patch of the slow slip event, and we can compute the elastic Green's functions that allow us to take displacements at the surface and project them onto the fault interface. And so we do that here, and you can see now that all the amplitudes of slip now align. So we think we've done a decent job over the 6-month-long slow slip event of projecting the surface displacements onto the subduction interface at depth. All right. So you can see here that the low frequency earthquakes are happening, map view or in the depth profile, are happening on the down dip edge of this slow slip source region. All right, so what happens if we look at those low frequency earthquakes and we try and convert them, just going from counting events to actual estimates of fault slip on the interface. So we can go to our equation of seismic moment, and we can see, it's just a product of the amount of slip, some shear modulus, and then the area that's actually slipping. And we can actually constrain everything ourselves, but D, so that we can solve or estimate D from our observations. So first, for the seismic moment, we can say that it's just the integral of the moment rates integrated over each of the low frequency earthquake source time functions, multiplied by the number of low frequency earthquakes we saw. So the geodetic data is sampled at 24 hours or 6 hours in our data set. And so we want to estimate the amount of seismic fault slip on either 24 hours or 6 hours so that we can compare the two. So we integrate the moment rates that we get from the low frequency earthquakes over either 6 hours or 24 hours. And so that involves two observations: seismic moment rate, which is dependent just on the displacement amplitude in the far field, and then the number of low frequency earthquakes that we see. We can then constrain S, or the source area, by making an assumption that the number of low frequency earthquakes active in any given time window is telling us about how many source patches are active. And so the number of sources that we see active in any given 6 or 24-hour time window is going to be proportional to the source area that's seismically active. And so by putting all these ingredients together, we can estimate the cumulative fault slip for this catalog over 2.5 years at either 24 hours in blue or 6 hours in orange. And we can see that they match pretty well. We have a slight difference of 3%, but for our intents and purposes, that's good enough. So now we have our geodetic fault slip. We've taken the surface displacements and projected them onto the plate interface. And we have a cumulative seismic fault slip from the low frequency earthquakes we observed. And so now we can try and connect those together with a very simple model. So the idea is that we're going to set up our model to be a competition between two different behaviors. One is going to be a constant loading term that is just stationary, will always march and in the direction of what we would expect for frictional loading. And then it's going to be competing against frictional release. So whenever low frequency earthquakes happen, we expect that there should be a release of that built up frictional stress. So we can define the loading term just as the long-term loading times time, and then there's some static offset just to get the y-axis right. And then the second term is going to be the slip rate, or the derivative of these time series. The integral of the slip rate as a function of time. We're just looking at the cumulative seismic study. And then the magic that makes this all work is this scalar right here that changes seismic fault slip into geodetic slip. So whenever we think about measuring something with geodesy at the surface, we're capturing the entire moment release, regardless of what slip rate it happened. Seismically, though, we can only see things that have slip rates that are fast enough to radiate seismic energy. Otherwise, we're blind to them. Typically, what we see when we see here almost 8 centimeters of displacement on the fault surface, that the cumulative seismic slip here you can see is just a tiny fraction. So that what that implies is that if there's this given source region of slow slip that's moving, low frequency earthquakes only occupy a tiny fraction of it. So there is sort of like a meter or a measurement point within this big source region telling us what's happening. And we're looking for the scalar that takes that little, 1 centimeter area of measurement and scales it up to the whole area of slow slip that's moving. So there's two free parameters. We can either mess with the loading velocity or we can mess with the scaling between a seismic to geodetic moment. So, you know, we don't go into this completely naively. We expect that the loading velocity should be the long-term plate motion that we know from, you know, geodesy at like a global scale. So we expect 6.4 centimeters of year in the central Mexican, the central segment of the Mexican subduction zone. So we can put that in, and we can then try and find the scaling that corresponds to that, and we can't fit the data. So here you're looking at the 24-hour time series, and here you're looking at the 6-hour time series. And we can't make it work. We can try and find the loading velocity that allows us to fit, but we get something that's 2 times what we would expect. So that also physically doesn't really make much sense. So our solution is very unsatisfying, at least for this presentation. We're just going to add a power law exponent to this term here. And we're going to basically ask what's the power law exponent we need so that any given amount of seismic slip is scaled to the correct amount of geodetic slip. And then we can make it work with this empirical relationship that for me is no longer visible. We can see that our 2 models, the 24-hour or 6-hour models, they fit well in time series. You can see these little bumps downwards when there's little slow slip events, and then you see this big excursion during the magnitude 7.5 slow slip event. So we can make it work, but the question is does it really make much physical sense? In the paper, and I won't get into this here, we go into how we think that this power law exponent of 2 that fits the data well is actually an approximation of 2 linear scalings, and that the scaling before the slow slip event and during the slow slip event is different. And the reason we think that the scaling is different is because the area of the slow slip is very different. And I'm happy to talk a little bit about that later if you'd like, but for our intents and purposes, we'll ignore that for now. And we'll just ask ourselves, now that we have this calibrated model, what does it tell us about the timing of plate coupling and slow slip activity on the plate interface? So to do that, this is why we did these 2 different time series solutions at 24 and 6 hours. Both solutions reproduce the large-scale geodetic record well. But there are differences that arise when you start to look at the smaller time scale. So you can see here, if we zoom into this little slip event, that the 6-hour one shows smaller slip than the 24-hour one. So we can start to ask questions about what that actually means. So what we can do is we can go back to our definition of coupling, and we're just going to take, I'll show you real quick. We're going to take the 2 models that we have, and we're just going to take their derivative. So that's what's plotted here. This is simply the derivative of the models that we were just looking at. In blue, once again, we have 24 hours, and in orange, we have 6 hours. On this axis, you see we call this instantaneous fault coupling, because we're basically measuring the coupling of every single time step of our time series by just dividing by this denominator. We're normalizing what we see. You can see that you can easily convert this into slip rate, or we measure this as slip rate, and that slip rate can either be positive for fault coupling, or below or negative when it goes uncoupled. And we can click this Y scale, it actually goes down way down here, because it uncouples much faster than plate coupling would suggest. All right, so what do we do with this? The first thing that we see is that if we look at this, most of the time it's fully coupled. That's sort of explicit in the model because we say that there's this constant loading, but kinematically it explains the data quite well by only having very small moments when slip happens and the plate interface actually uncouples. And this unlocking is sporadic and transient, just like the low-frequency earthquake activity would suggest. And if we zoom in on one of these little slip events that I pointed out earlier that had this difference, you can see in blue here, you have this sort of, smooth excursion. You can see your slip rates get to like something like 60 centimeters per year in the opposite direction of plate loading. But if you look at the 6-hour time series, you see it's very spiky. And with both of them, we can explain the data. But this would suggest that if you only look at 24 hours, you're missing some of the details of these dynamics of how it actually happens, because the geologist can't tell you anything more than what the sampling rate that you're using. But if you go to 6 hours to a higher sampling rate or shorter timescales, you're able to explain the data just as well, but with a much more intermittent evolution of slow slope. And we can also start to understand what these, amounts of what partial coupling might mean. Because typically, if you wanted to estimate coupling over the GPS time series, you have your big slow slope event here. So you take this as your time period over which you estimate your linear trend or your velocity. And you would find, you would expect here to be something close to fully coupled. But when you average over all of these little transients, even if they only last a little bit of time, you find that you only get 60% coupling when you use a 24-hour time series. And if you go to slightly shorter time scales, that coupling increases. And you get 71% with the 6-hour time series. So, one takeaway might be that partial coupling, when estimated from geodesy, might just be the result of us averaging over long time windows that can't capture the dynamics of what's actually happening on the plate interface. All right, so in the last 10 minutes or so, I'll tell you a little bit about our most recent work, looking at, trying to think about what controls the dynamics that we've just been talking about. So I've already showed you this multiple times now, but the point I want to make that I want to start with here is that these low frequency earthquakes, they are always characterized by these clustering or these swarms that happen in these punctual bursts. And I've shown you earlier that when this happens, we can explain the geodetic data by suggesting that this is when the plate uncouples and there's slow slope happening. So what we can do is we can make a very big assumption. And we can say that if the timing of these bursts are a little messy, but we're just going to assume they have a single recurrence interval and a single duration. And we're going to try and measure these two timescales of slow slope. So here is our two example families over 5 years from Japan. So we're looking at the recurrence interval of these two low frequency earthquake families. One of them is slightly deeper than the other. And we can see different behaviors. The shallow one has these very punctual bursts. And my assumption of a single recurrence interval and a single duration almost makes sense when you look at this data set. If you go to a deeper family that's more continuous, we see that it's a little bit trickier for that assumption to hold. But what we can do is we can quantify this behavior by just counting the number of LFEs in a given time minute. So we're just counting, I believe here it's every 4 hours or 6 hours or something like that. And so you get this messy, what we call the event count time series on the bottom of that plot. And we get one for each of these families. What we can do then is we can take the autocorrelation of this time series. You take 2 copies of it and you move one of them and you land and you just calculate how much overlap is there between these two histograms. So of course you're going to get a very strong peak at 0 lag. And as soon as you start shifting one of those time series, you're going to lose power. Now everything doesn't lie on top of one another perfectly, but it's going to lose power with some sort of decay. And that decay is telling you about the duration, the average duration of these different low frequency earthquake swarms. So we can measure that duration by measuring the width of this central peak in the autocorrelation. So that gives us one time scale that we're interested in, measuring the duration. We can do this for every single low frequency earthquake family. The second thing that we can do is, if there really is some nice recurrence, as we continue to slide our autocorrelation, or as we continue to slide our event time series to compute that autocorrelation, it's going to decrease as we get into this space in between forms. And then at some point, it's going to go back up. Because now we've shifted this swarm over enough to hit the other swarm, and now we get another peak of activity, or a peak of power in the autocorrelation. So we can measure the recurrence interval of this sort of average, recurrence interval of swarms by the autocorrelation, by trying to find this peak. But it's a pain in the butt, and it's tricky because it can sometimes be noisy if you don't have enough events. So instead, what we can do is we can just calculate the Fourier spectrum of this autocorrelation, and we can pick the recurrence interval as the peak of that, the period of that peak. And anything that has any Fourier spectrum that has any sort of periodicity is going to increase in power as a function of period. So you hit that periodicity, and then the power falls off because there's nothing. There's no, cosine sine wave that explains that frequencies at longer periods. All right, so we can measure this duration recurrence interval at 4 different boundaries. So we have 3 different subduction zones, Cascadian, Ankine, Guerrero, and then we can also look at part field section of the San Andreas Fault in California. So the part field is of course, a transform fault, and so here everything is just aligned in depth. There's no real geometry to look at here. But already, if you just look at this, you can see that the low frequency earthquakes are distributed across a broad range of depth. So here I just plotted part field as a vertical line, and then these are the profiles of slab 2.0 in the 3 other zones. And if we look at how the sort of average behavior that we see of these different low frequency earthquakes, the ones that are shallower in darker colors have much more step-like behavior that we saw here, with these very well-defined punctual bursts. And then if you go deeper along the subduction interface, you find that the steps are much more frequent. You can see, like someplace in Parkfield here, it looks like they almost happen all the time. We're not the first people to have observed this, but this is just, this behavior that is dependent on depth that we see in every place where there are low-frequency earthquakes and slow. And so we want to measure the duration and recurrence interval in the way I just showed you as a function of depth in these 4 different places. So that's what we did. So here I'm showing you as a function of depth the 4 different plate boundaries, and we're looking here at recurrence interval and duration. So just as a reminder, this is the recurrence interval duration of this single characteristic cycle of slow slip that tries to explain the data. And what we see is that there's this monotonic decrease in every single zone of both the recurrence interval and the duration. And what I find really cool is if you take these 2 things together and you plot the recurrence interval as a function of the duration, you find this linear scaling. And every single region will have a slightly different linear trend in here. So be it, there's obviously going to be differences between these 4 very different plate boundaries. But you could probably fit some big fat line through there, and you could, fit all of them to the same trend. And you'd find that on average, recurrence intervals of slow slip are 35 times longer than their durations. That's just the scaling that they behave at depth. So now we can try and interpret these results with an episodic model of fault motion. So we're just going to start here with the x-axis of time and the y-axis of slip. So here, nothing's slipping because we're frictionally locked. Then all of a sudden, we're going to have a slip event, and it's going to lock again, and this cycle is going to repeat. And every single one of these times where the slip jumps, we're going to have a slow slip event. So we can define our 2 time scales as the duration of a slow slip event, and then the recurrence interval. Sorry, it's wrong. It should be at the beginning. From the beginning of one slip event to the beginning of the next one. So that duration is encompassed, is part of the recurrence interval itself. So we can define this very simple slip budget model, where we say that if we were to draw a line through here, and we were to estimate, let's say, a long-term velocity, just like we would do for genetic time series, we have VL over here. On average, that's going to give you the amount of slip over the recurrence interval. And that needs to be balanced by the actual slip you have during this duration here. So this duration times some slow slip rate. And the duration, the slow slip rate, and the recurrence can all depend on depth. And we expect that the long-term rate does not depend on depth. We assume here, so for max this would be 6.4 centimeters per year, and cascading would be like 4 centimeters per year. We measure these two things, right? So now we can solve for this. So we can estimate the slow slip rate as a function of depth in all these 4 different places. So that's what we have here. So you have slow slip rate in centimeters per day on these 4 different plate boundaries as a function of depth or pressure. And you can see that there's some scatter, but there's no real systematic trend. And you can notice here, typically when we think of slip rates, you plot them on logarithmic scales because things vary quite a bit. Here it's on a linear scale, and we're looking at something that's on average about 0.6 centimeters per day, with some sort of factor of 2 variation around that. So in like geophysical terms, we're pretty much seeing the exact same thing across all different depths, suggesting that the slow slip rate is constant across 4 different plate boundaries and does not depend on depth. So this would suggest that there's some sort of single mechanism that controls slow slip across all these plate boundaries. And we can also probably guess that whatever that mechanism is, it's probably not very sensitive to pressure because it spans a wide range of depths and more than a gigapascal of pressure. What we can do is we can translate this to temperature via thermal models. So here you can, as a function of pressure and temperature, you put your subduction interface here, your plate interface, and we show here where low frequency earthquakes have been observed. And so it allows us, right, given pressure, to translate to temperature for each of these different plate boundaries. So we can do that. And what I've done here is I tried to keep these axes consistent. So this is showing you the range of pressure that we observe. And then we're basically making a box around all of the thermal models that contain our low frequency earthquakes. So the thought is that this temperature axis corresponds to this pressure axis for this group of thermal models. So we place here, we're looking at the same variation that you might expect if you had a thermal model that went straight through. And you can see that we're able to collapse all of our observations of this constant slip rate into a much narrower range of temperature. So that's the first takeaway, is that we see the low frequency earthquakes, the same behavior over a narrower range of temperatures rather than pressures. And what's sort of fun about this is if you look and say things mostly happen at about 400 or 425 degrees, that's where low frequency earthquakes start as a function of temperature. And you go here, I should put the citation, this is the classic Hacker, Abers, and Peacock paper from 2003 that looks at the metamorphication of just standard moor or mid-ocean ridge basalt. And you have this very stark difference between the water-bearing minerals. So dark colors mean they have mineralic water trapped within, that then dehydrate due to metamorphism as you increase in temperature. And it's relatively insensitive to pressure. Because you can see that all of these boundaries between the darker and the gray and the lighter gray are almost pretty much vertical. So you expect that this dehydration reaction that would change the oceanic crust as it subducts would be sensitive to pressure, sensitive to temperature, not to pressure, which is exactly what we see for the low frequency earthquakes. So we would suggest that this constant slip rate, that remember, actually represents a wide span of dynamics, different recurrence intervals, different durations, that all of this depends on temperature. And so what we think our interpretation of this is, we take a step back and we tell ourselves that slow slip sits within this transition between this brittle frictional earthquake behavior, this quasi-continuous creep that we often think of as viscous creep, it sits in this transition between the two. And slow slip ends up exhibiting characteristics of both of these two end-member regimes. So here, if you think about the dynamics, both earthquakes and slow slip are episodic, whereas creep is continuous. You would think earthquakes to be brittle and creep to be viscous. Earthquakes could be controlled by pressure, but temperature to control both slow slip and creep. And so you sort of end up in the middle here, where you think that slow slip should be some combination of frictional and viscous behavior. So it exhibits the episodic dynamics of frictional sliding and the temperature dependence of like a viscous creep law. And our sort of thinking behind this is that the frictional component allows us to build up elastic stresses without anything moving. And then as soon as that breaks, the viscous component controls the relaxation time and keeps the fault slow. So as soon as that stress reaches that failure threshold to have slow slip, the viscous component, and remember this very heterogeneous subduction channel, then puts the brakes on that frictional slip to keep it slow, and the temperature controls that time scale over which that slow slip happens. So to wrap up, geodesy alone, I think, lacks the resolution to capture the short time scale dynamics over which we see slow slip and low frequency earthquakes that happen. We can use seismic activity and low frequency earthquakes as an opportunity to probe the timescales and mechanics of the fault motion we see in this deep zone. Kinematically, we can explain the geodetic time series with these very intermittent episodic sort of coupled, uncoupled plate behavior. And we don't necessarily need to appeal to partial coupling to explain kinematically our observations. And then if we go to what the geologists have been telling us now for more than a decade, for more than several decades, is if you look at the exhumed outcrops, you see this mix of rheology and deformational mechanisms. Low frequency earthquakes and slow slip are happening in this finite shear zone at the subduction channel. And there's this unique environment where there are pore fluids involved that can potentially enable frictional slip that would otherwise be impossible, that would then interact with this viscous component that's dependent on temperature. And so here we presented geophysical constraints on these timescales that help us sort of tease out that maybe temperature is what controls the timescales of the slow fault motion. That's this interplay between frictional viscous behavior. With that, thanks so much for listening.
¿Tiene alguna pregunta? No. Well, obviously from non-specialist. Of course. And you are talking about native, and you're examining this interface which cannot take up an arbitrary deformation. So my question is, this deformation could be transposed to the wedge of the overlying plate. Because if you look at the plate, perhaps you can even see this cycling, there's a build-up and this release toward the trench. And well, that's my question.
No, I think it's a very good point. So, as a geophysicist, all of our faults are planar. And they lack that third dimension. But you're right that finite shear zone has to encompass not just oceanic crust, not just entrained sediments, but probably also some portion of the upper plane that's being underplated and sort of dragged into this whole mess as it subducts downwards. So in this interpretation, I would say I would have no horse in that race. And that if there is some part of the upper plate that's involved, it's part of that sort of subduction channel that's accommodating all this deformation. So over what fault width you integrate the slip so that you can match the long-term constraint of, in Mexico, 6.4 centimeters per year is a good question. I don't have the answer to that. I would just assume that we're integrating over what we need to conserve that slip over the long term. But it could very much, involve not just the oceanic plate, but also some portion of the upper plate.
Because there's great slip transfer from the conversions to the upper plate.
And so there can be inelastic deformation that can also be represented. And so here we're making the assumption that there's everything, once you integrate, once you go away from the plate interface, everything's elastic. In that sense, everything's conserved, but I will totally concede the point that that is not going to be a valid assumption. But at least for what we're working with here, we have to operate with the constraints that we have.
So during the first part of the presentation, you show that metric that relates to the velocity, expected velocity.
Yeah.
And based on that, you are determining whether you have plate coupling or right?
Yeah.
So how will constrain are the expected velocity? Because it seems that is why.
That's a great question. I think that goes into also the question of how much inelastic deformation you would expect. Because when we make the assumption that what we solve for at the surface in these sort of plate reconstruction models where you're moving these plates around over millions of years and you're trying to constrain the relative motion, you're assuming that whatever you see at the surface is what has to happen at depth. But there might be some inelastic component that contributes to that. And here we're ignoring them. I would say most people ignore it, at least in geophysics. But it's a good question. So how well constrained it is? We've been observing pretty stable velocities with GNSS networks around the world for a long time. But we're only capturing a very tiny portion of whatever earthquake cycle you're thinking. So I've had questions about, we're down dip of the trench, but what happens on the other side, in the incoming plate? What sort of deformation happens there as that plate starts to bend due to the negative buoyancy in the bend? That's something we have no control over. That, seafloor geodesy might be a fun way to do that, where you could try and measure if there's shortening of that incoming plate on the other side of the trench. That I think would be quite important for sort of the geodynamic constraint over what's happening here. But we're not there yet.
So perhaps a comment. I would say this is the motion of the ocean plate is pretty well determined. There are only a few places on Earth but I agree that we get closer to the trench. You don't know exactly what's happening. And on the continental side, I believe the main problems are the deformation of the continents, the motion of seabird, when you have a big subduction whole thing. And taking that to account, either in New Zealand or Colombia is difficult.
Yeah, because every time you're going to have to, every time you take your geodetic measurements across that forearc into the stable plate interior and you're looking for this gradient in motion, you first have to remove, the tectonic signal that we expect from a frictional level. And so if we can only resolve that as well as we can't piece apart what the different components of that surface motion is. So we start with models at least, how well they work. And they surely can't be correct, but.
So if I understood correctly, can you go back to the sort of the stepwise picture that you had?
Of the different LFPs?
No, no, two of the ones. No, the other way around.
Down?
That one.
Oh, yeah.
So, if I understand correctly, this is a long and simple subduction time. As you go deeper, your duration gets shorter, meaning that the recurrence interval gets shorter.
It also gets shorter, which is not what you would expect.
Right? So, if you go not down, what you would see is just too many little steps that
It becomes continuous,
So would you continue?
like we expect creep to be.
In some way, thought that down there you would see a continuous because there's no coupling.
Yep.
And then you start seeing those little steps, and you start seeing steps that are longer and longer.
So we had a really cool idea where you can just extrapolate these down to 0. And that's where you would expect the depth, which becomes continuous.
For the footnote coefficient.
Where it's full, we're in a full creep regime. And how cool would that be if you could project these to 0, convert to temperatures with the thermal model, and you find like one temperature. It doesn't work.
On the thermal models, you have to have a frictional coefficient of when it's stopped being.
Yeah, when it becomes steady state. Yep. So we tried that. I don't know, you get like a temperature that's within like 100 degrees of everything. But I mean, maybe in the grand scheme of things, that's actually pretty good. Because remember, our thermal models here obviously have to be crappy, right? Just like all of our geophysical models of what's happening closer to the surface. Like if you look here. So like Nankai, if you offset it by 50 degrees, just because the thermal model is wrong, it lines up incredibly well with the rest of them. Cascadia actually here is we updating the figure. The low frequency earthquakes we have in Cascadia, there's just 8 families, and they don't sample the whole tremor region. So it actually looks much better when you extend this. So you use the LFEs that you have to estimate the slip rate. But then you extend this solid line to the extent of which you actually know tremor happens. And it actually lines up extremely well. So if you extend Cascadia to where we know tremor happens, and then you say Nankai has some, arbitrary 50% off, 50-degree offset, everything lines up like almost perfect. But I mean, those are the uncertainties in which we're working with. So the thermal models depend first on that long-term convergence rate. It depends on the structure, whether there's any bending of the plate as it goes down. So there's all sorts of things that could change that.
Yeah, go ahead.
Two questions. So the first one is I just want to make sure that I correctly understood. So basically the idea is that the magnetic interface is not creeping at intermediate velocity between 0 and infinity, but that there are parts that are fully locked and starting to move. So that's probably what you see with the low frequency earthquake, but you said that the area involved is much wider.
Yeah.
So if it's wider, usually the geodetic inversion would involve an area which is much larger than the one seen by the tremor.
Yeah.
And even there is a suggestion that the tremors are rather at the edge of where you have slip. So it suggests that the relationship between the two is with the shear stress rather than the slip itself.
So I've seen there is this very cool paper by Baptiste Rousset that looks at the slow slip offshore Japan in the Bozo region that models the propagation of the slow slip and shows how earthquakes happen at the edge of that slip boundary, suggesting that's where you expect the shear stress gradient to be the highest, and you would then trigger those earthquakes there for that reason.
Yeah.
I don't necessarily know if I'm aware of observations that show that LFEs and tremor happen at the edge. I think there are observations of propagation of tremor that looks like it sometimes can lead to slip, but you'll also have ruptures behind a slip front. So I think there might be something there where shear stress might be playing into triggering them, but I also know you have activity behind the front as well. So for example, the easiest example in Mexico is you have this huge slip region that's being activated for slow slip, but you have low frequency earthquakes zooming up and down that source region constantly during that 6 months. So it's not just the slip front.
And my second question is how general with these kind of slip model, because if we look at South America, most of the slow slip area that we have shallower, so lower temperature, and they're also synchronous to regular energetic impulsive earthquake. You can see the repeaters and the family being activated as the slip propagates. But it looks like perhaps the phenomenology might be different because you have larger also earthquakes, the ratio over seismic might be different. You see some interaction and acceleration after larger event between storms. And I'm also wondering, when we see creep observed at a certain place, we really see creep. If you put a piece of paper, you will probably see some variations, but you're not going to see the stick and no, so perhaps the slip might be different things.
So I think there is, and we're dealing with a reviewer who has no, but I think that there is a real dichotomy between deep slow slip, down dip of the seismogenic zone, and up dip slip that's shallow, closer to the trench. Because in every, and I might be reductive here, but I think in every example I've seen, when it's clearly down dip of a locked zone, we see and we see the sort of slow slip and low frequency earthquakes together. But when it becomes sort of nebulous about where that locked zone is and where the slow slip happens with respect to it, so like Jicaranqui or like in Chile, in the Copiapó region, it's not so obvious. And so in there, you don't see low frequency earthquakes or tremor, you see mostly earthquakes. And so I do think there is some difference between what happens down dip of a lock zone and what happens up dip in the sort of, 20 kilometers and above depth range. So that's just phenomenological. I have no idea why that would be the case, but it would suggest that the processes are different. Just like there's lots of models that have been proposed to make slow slip slow. I think there's lots of different ways we could have slow slip. And what happens in this deep transition zone from frictional to viscous behavior might be different than what happens on the opposite side of the cyclogens. Might be multiple ways to make it slow. But I don't have a satisfying answer. But already, at least, we're happy that we've been able to take these 4 different plate boundaries that are all very different. Different thermal structures, different lithologies. One of them is a transport plate boundary, and we see the same thing. But we are within that deeper transition zone down dip of the lock. That's what Joe was saying.
Great. Let's thank Will.